So last week, we defined a topology and we defined what it means to converge for a sequence based on a topology. This week, we define a distance function. And the good news is that when you have a distance function, so you have a metric space, when you have a metric space, you have a topology. And I will explain to you now how you can build a topology based on a distance function. So let's start with a distance function. In other words, let's start with a metric space. So E is a set, D is a distance function on this set. Given a point X in E, we can define an open ball around X with radius R this way. The ball centered in X with radius R is all the points Y such that the distance between X and Y is smaller than R, and it's strictly smaller than R. In other words, what is on the boundary, what is equal to, when the distance is equal to R, it is not on the open ball. So if you want to think about the open ball in R3, that is an open ball. In other words, it's like a ball without the boundary, without the sphere around it, because it's strictly smaller than R. If you think of the plane, then the open ball will be the disk without the circle. It will not have the circle in it. It's the disk without the boundary. And if you are in R1, in the line, then the open ball will be the open interval centered in X. So it will be X minus R, X plus R, and X minus R, X plus R are not included in this ball. So this is the way to define an open ball of radius R centered in X. And I can think of Rn, but you can define an open ball for any metric space. So all you need is a distance function. And the distance function is any function that meets all of the criteria we talked about in the previous videos. Now that we have open balls, we can define a topology based on these open balls. Let us define the topology this way. I can define a topology based on the open sets. Remember, a topology is the set of the open sets. So let me define these open sets. An open set O will be such that for any point in O, there will be a positive R, actually a non-negative R, which means positive but not zero, such that the ball centered in X with radius R will be included in O. So let me say this again. Set is open if for any point of the set I can actually put in the set a ball of radius R centered in X. I want you to prove that with this definition, T that I just defined is a topology. So go back to the definition of a topology and check that every criteria is met. Okay, let's do it together. So my topology is defined as all the sets O, open sets, such that for any point in the set, there exists non-negative R, such that the ball centered in X with radius R is included in O. Let's admit the first criterion of a topology, the empty set and X elements of T. Well, the empty set, does it verify this? Is it true that for any element of the empty set, there exists a non-negative R such that the ball centered in X with radius R is included in the empty set? The answer is yes. Because for all X in the empty set, anything is true, because you will not be able to find any X in the empty set. So if you ask the question, is it true that for any X in the empty set, X is blue? The answer is yes. Now, X, the whole space, is it an element of T? The answer is yes. If I take a point, if I choose a point X, any X in capital X, then I can basically choose any R, and it's going to be true that BR of X, the ball centered in X with radius R, is included in X. So the first criterion is not difficult to prove, to verify, to check that indeed T will meet this criteria. Second one, is it true that any union of elements of T is in T? Well, if I choose two open sets defined this way, and I basically take the union of this set, well, if I choose a point in the union, I will be able to include a ball around this point of radius r, and therefore it will also be included in the union. So it's not difficult to prove that the second criteria is met. The third one, though, is a little bit more tricky because you're going to have the intersection of two sets, or actually a finite number of sets of T. Now, this is where it's a little trickier, because if you choose a point in the intersection of elements of T, then it will be a point of every element of this intersection, which means that you will be able to find a ball centered in X with radius R1 for the first one, R2 for the second set, R3 for the third set, and so on and so forth. You have a finite number of Ri's, R1, R2, R3, all the way to Rn. Because it's a finite number, you can choose the smallest one of these numbers. Let's call it R. Now, the ball centered in X with radius R is going to be included in the ball centered in X with radius R1. Also going to be included in the ball centered in X with radius R2, and so on and so forth. So what you have is that this ball centered in X with radius R is going to be included in every single set that I started with. So the intersection works. All right? So what we have is that T is a topology. All right, so when we have a metric space, we can derive a topological space. That is simply using the definition I just gave you based on the open balls. And this topology is a Hausdorff space, which means that it has some properties. That is that if I take 2 points, then I can find two open sets around this point that don't intersect. You can verify this very easily by just checking the definition of the topology I just gave you. And for those of you who chose to look at the PDF files that are associated with the video, you can actually verify that not only is it a Hausdorff space, it's also a normal Hausdorff space, which is a little bit better. Now, I can go from metric to topology, but I cannot go back from topology to metric. Or as a matter of fact, sometimes I can start with a topology and find a metric such that the metric space will provide this topology, but sometimes I can't. When I can, the space is called metrizable. And when I can't, well, it's non-metrizable. So if I have a metric space, I can always derive a topology. If I have a topology, sometimes I can find a metric space, a distance that will provide this topology. Sometimes I can't. I'm going to ask you to find a topology which is not metrizable. In other words, I'm asking you to find a topology that does not derive from a distance. All right, the trivial topology is an example of topology which is not metrizable. And just as a reminder, the trivial topology means it's the topology with the empty set and the full set. You won't be able to find a distance function that will provide you a topology which is the trivial topology. And if your topology is not Hausdorff, then you have no chance of having a topology which derives from a metric space, because as we said, if the topology derives from a metric space, from a distance function, it will be Hausdorff. So obviously, any topology which is not Hausdorff, as there's no hope, it will not derive from a distance function. Now, just because it is Hausdorff is not sufficient, but at least it has to be Hausdorff.